This was a reaction that was observed. There were some things about this reaction that weren't very well understood at the time of its observation. There were some questions that chemists arose as they watched this reaction proceed. One of the questions that they had was, why does this reaction not proceed at room temperature in the dark? Why does this reaction need heat or light? And another question that they would come up with, that they came up with while they were looking at this, is of these 5 different products, they're really just 2 organic chemists, just 4 important products, the chlorinated methanes, which of those 4 products was the most stable? Which one was made in the highest yield? Which was the preferred product of this reaction? And we can look at this equation and the way that it's balanced and understand the concept of really basically how these 2 molecules come together to make all these different products. But until we really understand the mechanism of the reaction, the very detailed pathway in going from these reactants to all these different products, until we can really figure that out, we're not going to know why the reaction needs heat or light, and we're not going to know which of these products is preferred and which is the most stable. As synthetic chemists, it's important for us to know whether or not heat or light or other types of catalysts are necessary, and to know why they are necessary. Because, if we can't provide heat or light, can we come up with an alternative catalyst that's going to accomplish the same thing? To answer those questions, chemists made several observations. Their observations were, number 1, the reaction just simply does not go when it's dark and at room temperature. This, of course, doesn't answer a question. The question is, why does the reaction not proceed at room temperature in the dark? The answer is not, the reaction doesn't proceed. But this observation of knowing that it literally does not go at all in the dark at room temperature. It's not just that it gives low yield or is not very, is slow or something along those lines. It just literally doesn't work. The second observation they made was that the reaction is most effective. You get the best yield when the light is absorbed by the chlorine gas, Cl2. So if you are using light and you focus it, really focus it on the chlorine reactant, not on the methane or not mixing it up, dispersing it or whatever. If you really shine a lot of light on the Cl2, you're going to get great yield of products. And the third observation that they made was that the reaction has high quantum yield. We're not going to spend a lot of time talking about exactly what quantum yield means, but in a nutshell, what it means is if you start with a very small number of photons, like just a tiny bit of light, you're going to end up with a very high yield of product. So it doesn't take a whole lot of photons to get this reaction to go. you can put in just one photon and get way more than one product out the other end. These observations helped the chemists to understand the reaction mechanism for the chlorination of methane. So we're going to write some study questions. What is a mechanism? I think that's really all that we need for this introductory section. And you should give yourself about 2 minutes to write a short summary for this section. It doesn't need to be too big.